beneath the ocean floor, something incredible is happening. Europe is quietly engineering the longest underwater tunnel in human history, a feat so ambitious it makes the Channel Tunnel look easy. Stretching beneath turbulent waters and unforgiving seabeds, this groundbreaking megaproject could redefine travel forever. But how on earth are they pulling it off? Let's dive in and uncover the mind-bending secrets behind the world's most ambitious underwater tunnel. The Fehmarn Belt Tunnel, a groundbreaking infrastructure project, is being constructed beneath the Baltic Sea to connect Germany and Denmark directly. Currently, travel between these two nations involves either a prolonged land route circling around the Baltic or a 45-minute ferry ride, significantly limiting efficient rail transportation. Recognizing the need for improved connectivity to enhance economic and logistical integration between Scandinavia and mainland Europe, Germany, Denmark, and the European Union have embarked on building the world's longest immersed tube tunnel. The tunnel will span approximately 18 kilometers, dramatically reducing crossing times to just 10 minutes by car and 7 minutes by rail, significantly benefiting trade, tourism, and daily commuters. Strategically located in the Fehmarn Belt, a historically challenging stretch of sea, the tunnel will streamline traffic flow across one of Europe's busiest transport corridors, reinforcing economic integration and cooperation within the region. This innovative project is not only a vital transport solution, but also a symbol of Europe's commitment to infrastructure development, sustainability, and regional cohesion. Upon its anticipated completion in 2029, the tunnel will stand as a testament to European engineering prowess and international collaboration. The Fehmarn Belt Tunnel is set to become an iconic engineering marvel, redefining Europe's infrastructure landscape upon its completion. At a staggering cost of approximately $7 billion, this ambitious project will be the longest immersed tube tunnel ever constructed. Unlike traditional tunnels drilled through solid rock, immersed tube tunnels involve an extraordinary feat of marine engineering. Massive tunnel segments, constructed on land, are floated to sea, submerged, and seamlessly interconnected underwater. The Fehmarn Belt Tunnel comprises 89 colossal concrete elements, 79 standard, and 10 specially designed, each meticulously fabricated from reinforced steel cages and concrete poured in climate-controlled environments to ensure structural integrity and durability. Each tunnel element weighs approximately 73,000 tons, demonstrating the unprecedented scale and precision required. Once assembled underwater, specialized rubber gaskets create watertight seals between elements, a critical detail ensuring structural longevity and safety beneath the Baltic Sea. This approach offers significant flexibility, as the tunnel segments can subtly adapt to seabed conditions, enhancing the overall structural resilience. The engineering behind this landmark project not only showcases human ingenuity, but also represents Europe's capacity to execute complex infrastructure projects on an unprecedented scale, reinforcing the continent's commitment to technological advancement and sustainable development. The decision to construct a tunnel rather than a bridge across the Fehmarn Belt was driven by careful analysis and practical engineering considerations. Initial feasibility studies in the 1990s explored various options for connecting Germany and Denmark, including a conventional bridge. However, engineers encountered significant obstacles. The poor quality and depth of seabed sediments made bridge foundations prohibitively complex and expensive. Moreover, the 18-kilometer distance posed structural and logistical challenges that drastically escalated costs and increased technical risks. Thus, attention shifted toward an immersed tube tunnel, a proven but challenging solution involving submerging prefabricated tunnel segments into a trench excavated on the seabed. This method offered a more economical alternative with fewer geological constraints, allowing easier adaptation to underwater conditions. Additionally, a tunnel minimized visual impact, preserved marine traffic routes without height restrictions, and avoided disruption due to adverse weather conditions, common drawbacks of bridge structures. Ultimately, choosing a tunnel represented a strategic compromise balancing engineering feasibility, cost-effectiveness, environmental considerations, and long-term reliability. The Fehmarn Belt Immersed Tube Tunnel emerged not only as the most practical solution, but also as the most innovative, embodying Europe's ambition to push the boundaries of modern infrastructure development. The immersed tube method, chosen for the Fehmarn Belt Tunnel, represents a sophisticated yet practical engineering technique ideal for challenging underwater crossings. Unlike traditional tunneling, which involves boring through solid rock, this approach begins by excavating a trench along the seabed. Massive tunnel segments, known as elements, are fabricated on land with meticulous precision, using reinforced steel frameworks enclosed in specially poured concrete. Each of these immense concrete elements, measuring thousands of tons, is carefully sealed at both ends to ensure buoyancy and watertight integrity during transportation. Once fabricated, these elements are floated out to their designated positions over the underwater trench. Controlled flooding of ballast tanks slowly submerges each element to the seafloor, where they are guided into precise alignment using GPS and underwater positioning systems. Upon placement, specialized rubber seals, known as G-gaskets, provide a secure, waterproof connection between adjoining segments. Water is subsequently pumped out, leaving a fully functional dry tunnel environment beneath the sea. This innovative method offers substantial advantages. It minimizes disruption to marine life, reduces environmental impact, and allows construction under complex geological conditions. By adopting the immersed tube method, the Fehmarn Belt Tunnel demonstrates Europe's commitment to cutting-edge engineering solutions, setting new standards for future infrastructure projects. The Fehmarn Belt Tunnel's construction is remarkable not only for its engineering sophistication, but also for its sheer scale. This colossal underwater passage consists of 89 enormous concrete elements, each approximately 217 meters long, 42 meters wide, and weighing around 73,000 tons. Due to their unprecedented size and mass, these tunnel elements are fabricated on-site from smaller, manageable segments. Each element comprises 9 individual segments, assembled meticulously through a carefully orchestrated production line, beginning with the assembly of reinforced steel cages, which provide the necessary structural integrity for concrete placement. The production facility itself is immense, featuring vast halls dedicated to steel reinforcement, concrete pouring, and curing. Operations requiring precise climate control to ensure structural uniformity and strength. Workers handle enormous volumes of steel and concrete daily, transforming raw materials into segments capable of enduring immense underwater pressure and structural stresses. Once assembled, these elements are gradually transported to a specialized dry dock, flooded with seawater to float them out for final placement. This meticulous step-by-step assembly and transportation process emphasizes the project's complexity and scale, underscoring the logistical, technical, and engineering expertise required to execute one of Europe's most ambitious infrastructure endeavors beneath the Baltic Sea. The manufacturing process for the Fehmarn Belt Tunnel is an intricate and carefully coordinated operation designed to ensure structural precision and durability. It begins with reinforcing steel, the backbone of each tunnel segment. Raw steel arrives at the on-site fabrication facility where automated welding machines meticulously assemble large steel reinforcement panels. These panels are then shaped into extensive rebar cages, providing crucial tensile strength since concrete, though robust under compression, requires reinforcement to withstand tension. Once prepared, these rebar cages are transferred into massive production halls, where workers assemble them into segment forms. Each element of the tunnel comprises 9 segments, each constructed sequentially. The concrete pouring phase occurs within tightly controlled environments to maintain consistent temperature and humidity, ensuring uniform curing and maximal structural integrity. Special ducts within these segments accommodate tensioning cables, steel strands inserted after pouring and curing. These cables apply compression, enhancing the segment's strength and resilience during transportation and installation. The completed segments undergo rigorous quality control before being slid progressively out of production halls, forming a complete element. This meticulous process exemplifies precision engineering, blending innovative manufacturing techniques with high standards of quality control, ensuring each segment meets stringent requirements for safety, reliability, and longevity beneath the Baltic Sea. The assembly of tunnel segments for the Fehmarn Belt project is a highly structured, step-by-step procedure combining advanced engineering techniques with precision execution. Each tunnel segment begins as a massive steel framework, meticulously crafted from prefabricated reinforcement panels to form the structural skeleton. Initially, the reinforced steel panels, fabricated within specialized facilities, are methodically assembled into comprehensive cages comprising floors, walls, and ceilings, creating robust structural frames designed to withstand immense underwater pressures. Once these cages are fully constructed, they are placed into precisely engineered formworks, where concrete is poured to encase the steel framework completely. This pouring process occurs within climate-controlled production halls, ensuring a consistent curing environment critical to achieving the necessary structural properties. After pouring, segments undergo a controlled curing period during which concrete attains optimal strength and durability. Each completed segment, weighing thousands of tons, forms just 1/9 of an entire tunnel element. As segments are sequentially cast and cured, they are progressively pushed forward within the facility, gradually assembling the full 217-meter-long tunnel elements. This sequential, precision-based assembly ensures each segment aligns perfectly with its counterparts, forming a cohesive structural unit capable of safely spanning the Baltic seabed. The meticulous segment assembly process highlights the extraordinary engineering sophistication underlying Europe's landmark infrastructure project. A key innovation in the Fehmarn Belt Tunnel is its built-in flexibility, an essential feature given the immense pressures and natural movements that occur beneath the sea. Unlike rigid monolithic structures, each tunnel element in this project is composed of 9 individual segments joined in a way that allows for slight movement. These internal joints act like hinges, giving the tunnel the ability to flex and adapt to seabed shifts, thermal expansion, or dynamic loading without compromising structural integrity. This segmented design ensures that stress is distributed evenly throughout the tunnel, preventing cracks or failures that might occur in more rigid configurations. The flexibility is further enhanced by specially designed G-gaskets placed between each full tunnel element. These rubber seals compress to form watertight connections when the elements are joined underwater using vacuum pressure, a technique that ensures both stability and leak prevention. By integrating movement into the tunnel's design, engineers have achieved a rare balance of strength and adaptability. This engineering innovation not only accommodates the unpredictable marine environment, but also extends the tunnel's lifespan. The Fehmarn Belt Tunnel stands as a testament to forward-thinking infrastructure design, where precision, resilience, and adaptability come together to solve one of Europe's most complex engineering challenges. The sealing and submersion process is one of the most critical and technically demanding phases of the Fehmarn Belt Tunnel project. After each massive tunnel element, comprising 9 individual segments, is fully assembled, cured, and inspected, it undergoes final preparations before being moved into position for deployment. This process begins with the installation of bulkheads at both ends of the element, making it airtight and allowing it to float once the dry dock is flooded. A key component in ensuring watertight integrity is the G-gasket, a thick, rubber seal encircling the end of each element. When 2 tunnel elements are joined on the seabed, a powerful vacuum system pulls them together, compressing the G-gasket between them to form a durable, watertight seal. This precision seal is vital for long-term tunnel safety, as it must withstand extreme underwater pressure while preventing any leakage. Once sealed and floated, each element is towed by tugboats through a controlled channel into deeper water. From there, it is carefully positioned above the prepared trench on the seabed. Using a combination of ballast control and precise navigation, the element is submerged and aligned with previously laid segments. This seamless transition from land-based assembly to underwater installation highlights the project's exceptional engineering precision. The final placement of each tunnel element in the Fehmarn Belt project is a delicate, high-stakes operation that demands extraordinary precision. Once an element has been sealed and floated out of the dry dock, it is guided by tugboats into deeper waters and positioned above the trench prepared on the seabed. Before submersion, engineers double-check its orientation and alignment using advanced GPS and underwater positioning systems to ensure it will fit seamlessly with previously placed elements. With positioning confirmed, the element is slowly submerged by adjusting the internal ballast, carefully flooding compartments to control its descent. The tunnel element must land precisely within centimeters of its intended position, aligning perfectly with the adjacent element. Once lowered into place, a vacuum system is used to pull the new segment tight against the previous one, compressing the G-gasket to form a watertight seal. After placement, final checks are performed to confirm proper alignment, sealing, and structural connection. The process is then repeated for the next element, continuing the chain of segments that will eventually form the 18-kilometer tunnel. This methodical, modular approach allows for consistent progress while ensuring each piece of the structure meets the project's rigorous safety and durability standards beneath the depths of the Baltic Sea.